inversely proportional to volume for a given temperature. That creates isotherms. Talked about this on Wednesday. Again, energy is conserved, so if we have a system, the kinetic plus the potential plus any change in thermal energy will be equal to the change in energy in our system. So, but for thermal, we will what we're going to look at in this class is systems that are finite volume, or it's going to be changing volume, but a finite mass. There are also processes in thermal where you look at just a fixed volume. We won't consider those. We'll only consider situations where the system has a fixed number of molecules. We won't be looking at fixed volume, we'll be looking at fixed mass systems. I'm just going to go through very quickly. Our big equation that we're coming to is we're only going to look at systems where we're changing the work or the heat, and that will change the internal energy. So this will be what we call the first law of thermo, which really says that if you count for all the energy, energy doesn't change. Inside it may change forms, but the total energy in the system is fixed. This is all, as far as I want to go, it's a concept I want to look at. Force is equal to pressure times area. Remember that from last time, bad joke, think about Newton over a square meter. That's a Pascal, so it's the amount of pressure over an area. And so if we have a force and it moves a distance, we know that's work. We've defined work on a system as positive in our equation. So imagine our cylinder. I'm going to put it on its side now. And I'm going to define x to the right. And so we have our cylinder here. And here's our piston. And we're going to apply a force to that piston. And it's going to move some amount delta x. So we have force times that displacement. The force and the displacement are the same direction. That would normally be positive, but the pressure here, the gas, is applying a force in the opposite direction that's equal to our pressure times area. So our force is the pressure inside this gas times the area. And it is pointing in the opposite direction of the force that's being applied, the work that's being done. Everyone see that? So our work now, we're looking at, let's call this force 1, will be equal to the negative of the force 1 times the x. Because the work is done on the system, but the pressure is in, the force from the pressure is in the opposite direction of the displacement. So this will give us a positive work if we push in this direction. But our force is equal to what? Pressure times area. But AdX, in this case, isn't that the volume change that we just had? So this is also equal to the negative integral of P dV. So the question is, why the negative sign? Because the pressure from this, the gas inside is pushing out, but we define work as being done on the system, so in their opposite directions, and that gives us a negative sign in our work equation. Our work is really F, integral of F dot dx, since they're It works out that's true for any situation. So it could be a balloon expanding out in all directions. The work done on that balloon will be equal to the negative of its pressure times its volume, the rate integral of its pressure to change in volume. What we'll do on Wednesday is we will then say, what does that look like for different ideal gas processes? If we go to a constant pressure process, that integral becomes very easy because pressure is constant, and the integral is just integral P dV. P is constant, you can pull it out, and so the work done in a constant pressure or isobaric process is just negative P times the change in volume. The integrals become more interesting for adiabatic or isobaric, isothermal processes, and that's where we'll go on Wednesday. So when we do that, there's physical significance on the PV diagram. This would be a good thing to review before Wednesday. The work done on the system will be a function of that integral PdV, and it makes a lot of sense on those PV diagrams. There's a very obvious graphical interpretation. We'll look at that, and we'll do that quite a bit next week. Any questions about that? Thank you for focusing on it. Let's focus on what we really want to focus on, which is how do we get prepared for this. Let's go ahead and start with eye clickers. I'm not going to grade this, but I think it just helps us focus. So we're going to do 12 or 13? 12 or 13 here? 12. No.
More helpful
12. I haven't heard anything else.
One doesn't have the answer key posted.
What's that? The other both will have the answer key posted by the end of the day. All right, here you 12. Go that one. All right. The magnetic field at the point P points. So we have.
Close together with this.
What's that? Oh, I have to get on. I won't be grading it, but I think it helps you to remember if there's little pressure. Yeah. All right. Let's see how we're voting. And that is, in fact, the correct answer. How do we figure it out? We point our thumb in the direction of the current. We wrap our finger around the wire. The field is coming out above the wire. It's going in at B. Any questions? Let's go to question 2. Oh, you can change your votes. Three, 2, 1. All right, our right-hand rule, we have V cross B tells us that if this were a positive charge, the force would be into the page. The problem is, it's a negative charge, so the force is out of the page. Good. All right, 3. I don't know if it looked this way during the exam. So a conducting loop is halfway into a magnetic field. Suppose the magnetic field begins to decrease rapidly. What happens to the loop? We just have a piece of wire here, there's some kind of magnetic field, and magnetic field is decreasing rapidly. two-step problem. What's step one?
You have to figure out the current.
You have to figure out the current. Because there is a flux through this loop, and that flux is changing and is decreasing. Lenz's law tells us that the current will be induced to try to keep that flux from decreasing. So the flux needs to be into the board. We point our thumb in the direction of the board, we wrap our fingers in the direction of the current, and it tells us that to sustain that flux, the current needs to be induced in the clockwise direction. Now, that's part A. What's part B?
Figure out which direction the force is.
Figure out which direction the force is on the different parts of the wire. Lots of different answers. All right. We have I, L, cross B, force up on this wire. I, L, cross B, let's see, force down on this segment. So there's forces on these two wires trying to pull the wire apart. So it's trying to expand that loop, which kind of makes sense. That's another way to sustain the flux, right, is to expand the loop. Then we have I cross B. There's a force this way. I's down, B's into the page, so therefore there's a force to your right. So this loop gets pulled into the magnetic field. Again, trying to sustain that flux by pulling that field in so that the flux through that loop doesn't change. Does that one? All right, which statement is about the magnetic field inside the box is true about the path shown? It points out of the screen, it points into the screen, left, right, or the field is zero. And what's an important thing to note here?
It's negative.
It's negative. Yikes.
Still thinking. Yeah, still thinking.
So if it was a positive charge, which way would the force be? To the left, right? So we know that V cross B needs to give our thumb needs to be pointing to the left. V is up. Which way does the magnetic field need to be?
Charge.
Right. So for the negative charge to turn right, and for there to be a force on that charge when it enters to the right, then V cross B, if it were a positive charge, the force would be the left, so the field must be into the board. Since it's a negative charge, the force is actually to the right, continues to be to the right, continues to get circular motion or cyclotron motion in the clockwise direction. Any questions? Use your thumb to point the direction of the force for a positive charge. Point your index finger in the direction of the velocity, and your other fingers need to point in the direction of the field. Why does my thumb pointing to the left when the force is to the right? It's a negative charge. I was big on negative charges this year, I don't know why. Alright, we didn't cover this, so it's not going to be on the test. Alright, Ampere's law. Let's see, for Ampere's law, what do we need to know? We need to know the current inside the loop, and we need to know the direction of the loop. Three of those currents are inside the loop. Which one is not in the loop? This one here. So it doesn't matter. Which way is the loop? Are we doing our loop integral? They're going in the clockwise direction. So positive is into the page. Now, let's add up the currents into the page. We have 2 in and we have 5 out. So What is the, we know the integral, loop integral of d dot dl, mu times I, in this case it'd be the mu times, what is it? 2 amps minus 3 amps minus 2 amps equals to negative mu times 3 amps is equal to,
Not negative mu times 3 amps.
negative 3.78 Tesla Tesla.
Why is it?
Wouldn't that be negative mu naught times negative, and times negative 3 amps?
What's that?
Negative mu times negative 3 amps.
The negative came from the 3 amps.
I just, this cancels. The negative, so it's
Negative
mu,
3 amps.
mu times negative 3 amps or negative mu 3 amps?
But you had
should have a
negative-
on
You have
the-
negative mu already.
You shouldn't have negative on the.
Oh, yes, thank you.
Okay.
Thank you. Right. Question? Any other question? If I had the loop going the other direction, what would have happened to this sign?
Would have switched.
It would have been positive. All right, shown below are the cross-section of two long straight wires carrying equal currents into and out of the page. At each dot, show and label the magnetic fields B1 and B2 of each wire. Then show the net magnetic field B net at each point. Align the and scale vectors appropriately. If the vector is 0, label it as B equals 0. Alright, so this is very similar to one we had in the book with the magnetic field being 0 in the middle. I saw that answer a lot, but it's not the same as the workbook problem. What's different from this in the workbook problem? Alright, the workbook problem had either both currents going in or both coming out, I forget. So now I have wires going in different directions, the currents going in different directions. So, should I give you a minute to think about it, or just go for it? Alright, how do we find the field along the wire, around a long wire? Stick our thumb in the direction of the current. This is going into the board. You wrap, let's call this wire 1. B1 will be down. What about from this wire? B2 is also down. So the B net will be twice as big, also down. Yeah. What about at this point? See, current is in, we wrap our fingers, perpendicular. It's quite a ways away, so it's small. Smaller because we're farther away. This one, the magnetic field to the left, it's closer to be a little bit bigger. Use a parallelogram law. Any questions? If I wanted to calculate the magnitudes of those, how would I do that? We'd need to know the distances are. If we forgot what that, our formula was, and we lost our equation sheet, we could quickly remember Ampere's law. It's a loop integral of B dot dl, mu naught times I. Let's define B in the direction of the current of the magnetic field. As we wrap our fingers around by symmetry, B is a constant everywhere along that loop. It's in the direction of the loop, so our loop line integral will be just B times L. In this case, it will be B times 2 pi times R, the distance around the circle. So, if we needed to calculate the magnitude of the magnetic field, we could use that equation. If you forgot, remember Ampere's law, you can always derive it. If I now had a charge moving in this direction, could we calculate when the charge is at this point what the force on it would be, magnetic force? Yes, we could figure that out with Joseph Art's law, or I mean just QV cross B. If I wanted to find the force on this wire, I remember that the force is IL cross B. I can find the magnetic field from this wire. Now our radius would be the distance from the two wires. In which case, which direction would, here's the magnetic field V1, it's down at this point here. What force is there on the wires? On this wire over here. Current I is out at you, B is down, force is out. So if I have two wires, the current's going in on this way and then returning that way, what will happen to those wires if I suddenly turn on that current? They'll repel each other. When I was outside of Kaiser Trentwood where the rolling mill is, and as the metal goes through the rollers, it suddenly draws a lot of current. If you watch the wires outside Trentwood, when they're rolling metal, the wires will suddenly jump apart as the current starts to increase. So as the metal goes into the rollers, the wires, you can actually see the wires jump apart as the current picks up to supply the rollers. And I'm talking the big wires coming in from the substation. It's kind of interesting. All right. Determine the following vector products, dot products and cross products. Let's see, 8 times 5 is 40, I dot k is 0. So 8i dot 5k is 0. 8i cross 5k, 8 times 5 is 40, I cross k is negative j, so that would be negative 40j. J dot k, 0. Dot, 0. J cross k, positive I. Let's see, J cross I would be negative k. K dot negative k is negative 1. You guys make me proud. All right, a proton moves through a magnetic field B equals 4I plus 3k Tesla with a velocity of 8 times 10 to the 6th I meters per second. Determine the force on the proton. The biggest problem people have, a lot of people raise their hands and say, what's the charge on a proton? I had the charge on the electron on the equation sheet. E, right? What's the charge? They're the same, right? What's the net charge on a hydrogen atom? 0. The proton has the same charge as the electron. So the charge on a proton is E, positive E. The charge on an electron is negative E. So this is just an application of QV cross B. We've got Q, we look it up, it's at the E. So force QV cross B, Q will be E, and then we substitute in B, and we do our cross product. After the proton is done, and I'll post the answer to that. Any questions about what we do? At that point in time, it's just a product, cross product. After the proton is gone, a second proton moves through the magnetic speed with a speed of 8 times 10 to the 6 meters per second, but does not experience a magnetic force. What is the velocity of the second proton? What on earth am I asking for here? The direction, right? We know that the speed is that. What I really want to know is the direction. What do we know about the direction? There's actually two answers to this problem.
Either be going in the same direction as the magnetic field or opposed to it.
It has to be in the same direction as the magnetic field. So, what is the direction of the magnetic field? B equals 0.4 I hat
0.3
0.3 J hat K hat Tesla. So, what is its direction? How do we find the direction?
We're still grid.
You can do the grid. What's the easier way? A vector has a magnitude and its direction. We know that that is equal to b hat, right? Isn't b hat the direction?
Yeah.
So what's b? B is equal to the square root of 0.4 squared or 0.3 squared equals 0.5 Tesla. Therefore, b hat equals 0.4 I hat plus 0.3 j hat over 0.5
Yeah.
a hat, thank you. 0.8 I hat plus 0.6 k hat. So, our velocity is equal to 8.0 times 10 to the 6 times 0.8 I hat plus j hat k hat, thank you, meters per second. This is now in the same direction as B. I also accepted the negative of that. In fact, if you said both, I give you one. So, this is a very tricky way of saying, one, do you know that it's in the same direction, there's no force, and what's the easy way to find the direction of a vector? Find its unit vector. Determine the magnetic flux of a sphere with a radius of 10 centimeters of a helium nucleus, that's 2 protons. People again ask me what's the charge on 2 protons, it's the same shit. Do not locate in the center of the sphere. So we could set up this geometry, we could do a whole lot of calculus, or what have I asked? Net magnetic flux, what is it, folks? 0. Next problem. What's that?
You always tell the trick questions they're worth a word less.
Yeah.
I mean, I think that's what I
Well, I thought about making it with 10 points, but it would be 10 or nothing, right? I didn't like that either. So yeah, some of the trick questions I do give fewer points.
I noticed that just kind of was the rule of thumb.
Carl's on to me. All right, now we have the helium nucleus again. The charge is 2 protons. It's still 2e. It's moving along the x-axis with the velocity 8 times 10 to the 6 I hat meters per second. As the nucleus passes the origin, what is the magnetic field at the following 3 points? Let me do, which one do you want me to do? The first one is on the x-axis, so what's the magnetic field going to be? 0. Let's go to B, it's a little more interesting. What law do we use here? Biot-Savart's, what is it? Force equals, I don't have my equation sheet. Q over 4 epsilon? That's the
Q mu naught over 4 pi r.
Q mu naught over 4 pi r squared times r hat.
No, times the cross product of the velocity and the radius.
B cross R hat, isn't it? The other form would be R vector over R squared. Did I show you that one? Or did I give you this one? Give you this one. What is R hat? So R, where is R from? From the source to the object of interest. From source to object of interest. Where's the source on this problem? Origin. For part B, the object of interest is at 2j hat millimeters, or 0.002 j hat meters. Now at this point in time, we still need to find R hat. Which direction is R hat? J, what direction? It's the magnitude of R, 0.002 meters. And now we know everything, we can substitute it in. Why was 1 0? Because R is 0.002 in the I hat direction. Our velocity is in I hat direction. The cross product is 0. In front of the charged particle, the magnetic field is 0. It forms loops around it. In the direction, if we point our finger in the direction of the velocity, we can find the direction of the field outside that axis of its velocity will be loops. Any questions? The figure shows a loop with a radius of 12 centimeters and a changing magnetic field directed out of the page. If the loop's resistance is 1.4 ohms and the current is 2.3 amps flowing in a counterclockwise direction through the loop, is the magnetic field increasing or decreasing in strength? Determine the rate of change of the magnetic field. All right. So let's look at this. So magnetic field's out of the page. We have a loop. The current is which direction? Counterclockwise. The current's going in this direction. The current is creating a field out of the page. So is the magnetic field increasing or decreasing? It's increasing. Wouldn't the loop want to oppose that increase? And the current would be clockwise. So the magnetic field is decreasing. Has everyone figured that out? It's kind of this whole problem's backwards. It's a backwards application of Lenz's law. Because I told you the current and I asked you which way is the field changing. So you can think about it. If it's increasing, then the current would be this way. If the field is decreasing, then the current would be that way. So if the backwards part's bothering you, think about it the frontwards and say, if the field is increasing, which way would the current be? Is that way the current's going? Oh, no. If the field is decreasing, which way would it be? Yes. Now we've got it correctly. So the field is decreasing. Now, how on earth do we find the field strength? We have Faraday's law where the induced voltage would be equal to negative number of turns of phi magnetic dt. The number of turns is 1, so in this case, phi dt. We're really only interested in magnitude at this point in time because we've determined the direction. find out the rate at which it's changing. We need to find the voltage. Does it tell us the voltage up there? It tells us we can think of this now as a circuit. The resistance is, what was it, 1.4 ohms? 1.4 ohms. Our EMF is unknown, but we do know that the current now is 2.3 amps. So we know our E equals IR. Oh. So if we know that, don't we? So the magnitude of the E to T, which is equal to IR, so that would be 2.3 amps, 1.4 ohms. Really isn't that bad. It looks bad, but it really isn't.
So, whenever you see like a problem that says determine the like change in the flows of magnetic field, so that's when we're dealing with E equals negative D over DC here.
Whenever we have it changing through a loop, there will be an induced voltage in that loop
Right. So
equal to the rate of change of the flux,
so that's when you can,
magnetic flux.
that's when you can use the EMF.
That's when you can use Faraday's law.
I've had a long time to answer this question.
All right, now, what's that?
I've had a long time to answer this question.
It does, this one, now, we have, this is basically a motor. We have D in the upwards direction. We have I going in a loop. I'm not sure what's making that, but in a motor, there'd be some kind of something forcing that current to go around in that loop. What is the force on the wire forming the left side? I cross B is 0, that's good. What's the force on the right side? 0, all right, we've got that taken care of. What's the force on this upper wire? Well, let's figure out the direction first. I cross B, the force is out of the page. And the force down here, cross B into the page. So there is a torque now, because this, and it's about this axis right here. So we look at this, what did I give you a radius, didn't I? It's 4 centimeters by 4 centimeters. So, let's talk about what the torque would be. The torque up here, the distance is 0.02 meters. The force will be out of the page. So the torque up here will be equal to 0.02 meters times whatever that force is. And it will be, call that x, it will be the positive x direction. The force down here, into the page, again we have 0.02 meters. We'll find out it's the same force. Now the force is into the page. Again, the torque is positive around the axis is the bottom wire. Oh, did I say the axis for the bottom wire?
Axis through the wire on the left, axis through the wire.
Oh. So in that case, this is 4 centimeters. That's 0.4. Actually makes it a little. What's the torque due to this wire and this wire? About the bottom wire? 0. The torque about this one is that. And what's the torque about the wire on the left?
0.
It's going to be 0. Because these two cancel. Now, how do we calculate the force on these two wires? It will be equal to I L cross 1.024 meters. And if we define our directions, we do positive X, positive Y, the top wire, this would be in the I-hat direction. I will be, help me,
1.3 years.
1.3 amps. And then B is in the J direction, because we've aligned that correctly, 0.89 J hat.
So that was the torque we just.
That's the force on the top wire. On the bottom wire, it will look very similar, except that there'll be a negative here. Because the current is going in the negative X direction. And that will assign you, that will give you the correct direction then for your right force. Deep breath. We have time for one more on the other test if you want it, but the solutions are posted.
Is that saying that the radius is in the direction that I have?
This force here does not have anything to do with torque.
I'm looking at the I hat next to the 24.
This one right here? So the current in this top wire is in the